Okay, we're going to do some more examples of using Taylor and Mclaren series. So, T series and M series. I'm going to do the following example. Find the M series of the function 1 plus x to the k for any number k. Okay, so solution. If k was an integer, then this would be rather easy because we would just use algebra to expand this out, right? And once we expand it out, there would be a polynomial in terms of x, and that thing would be the Mclaren series of this function, right? So when k is an integer, we could expand out. And that would be the M series, i.e., if k was equal to 3, then we would have 1 plus x to the 3 is equal to 1 plus 3x plus 3x squared plus 1, right? Oops, plus, sorry. Brain broke there for a second. 3. And this itself is a polynomial, and this polynomial is a Mclaren series where all these other terms are all 0, right? So, something I haven't told you, but is a true fact, Mclaren series is uniquely defined. So this in itself is the Mclaren series of this function when k is equal to 3. But the question asks us to do it for any k, right? For any k at all. So what we should obtain is something which generalizes this thing, right? And as you probably know, we can do this for any integer at all, and then we can find out these coefficients. There's this Pascal's triangle thing where you do 1, 1, like this, 1, 3, 3, 1. And so we recover the coefficients of 1, 3, 3, 1 from this layer of the Pascal's triangle, which is the third layer because we have power 3, right? That stuff probably is very familiar to you. Okay, what is cool is that the machinery we've learned about is going to allow us to do that for any k at all. And it looks a little bit intricate, but it's not too bad. So now, for any k, what do we do? So our function, let's write it. Okay, and we're going to start to differentiate it to find the coefficients. So we're going to not discuss whether or not this thing actually does have a Mclaren series. We're just going to take it as a given, and then we're going to find the Mclaren series, and then we're going to talk about the radius of convergence of the Mclaren series. So we differentiate this thing. Differentiate again. And so on and so on. So if we take the nth derivative, what do we have? We're going to have k k minus 1. So notice when we take the second derivative, we stop here at k minus 1, right? So when we take the nth derivative, we'll go down, 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 and then we'll have k minus, and we won't be minus n, will be minus n minus 1. All right? And then we're going to have 1 plus x, and here we're going to have k minus n. And in the particular case where we do have k as an integer, then this thing would just stop. So all the derivatives would just vanish after a certain point. So for example, if k was equal to 100, after we took the 100th derivative, then we'd have 100 minus 100, and this thing would just be 1, and then we just have a constant, right? So then as we took the next derivative, we just get 0. So all the following coefficients, the 101th, the 102th, all these other guys just vanish, and that's why, in that particular case, when we have k as an integer, the Mclaren series gives back just an ordinary polynomial. Okay, so we are evaluating this when x is equal to 0, because it's the Mclaren series, so what do we have? We have f of 0 is 1. Well, we can just go straight down to here, right, because this is the general formula. And the nth derivative at 0 is this thing. It is k minus 1, dot, 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 k minus n, and it's minus minus 1, so it's plus 1. Okay, cool. All right, so it's very tempting to try and to write this in factorial notation, which I'm not going to do because k is not an integer. So if k was an integer, so I'm going to put this a little aside. Maybe here even. Then what would this be? Well, notice the following. If we take k factorial, then it is k minus 1, da 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 da, k minus n plus 1. And then let's change color. Okay, the next time will be k minus n minus 1, all the way down to 1, right? And then this thing here, is just k minus n factorial. So then we would have that this expression over here is just equal to k factorial over k minus n factorial, right? So that when we put things back into the standard formula for the Taylor expansion, sorry, for the Mclaren expansion, let me see if I can squeeze it down here. So the standard formula is this is n. Okay. Then we see that we'd have k factorial over k minus n factorial, which is this binomial coefficient that you're probably familiar with. Okay. Again, this is when k is an integer, because typically we define k factorial when k is an integer, and then it just stops here at 1. However, k is not an integer for the general problem, and then for k factorial doesn't just stop at 1. Well, say that again. What I mean to say is that this expression just doesn't stop, it just keeps going. Sorry, this expression here just keeps going, right? So k is not an integer, so if k was, say, 100.5, then this thing would just keep going past when n is equal to 100, right? And then we'd have something here which would be a negative expression. And that would be quite confusing to have a negative factorial. So instead of writing this, I'm not going to write it like this at all. I'm just going to keep it in this form when I write out the expression that we've learned. And I wish I had some space, but okay. Yeah, I just don't have space. All right, so okay, so what did we learn? We learned that when we take the nth derivative at 0, then what do we have? We have k minus 1, all the way down to k minus n plus 1, right? So when we do the Mclaren series, it'll be this. It'll be the sum from k is equal to 0 to infinity, k minus 1, k minus n plus 1 over, this is n factorial x to the n. Okay, that will be our guy. And if k is an integer, then this expression here can be written as k factorial over n factorial k minus n factorial, because this expression stops when n goes beyond k. Okay? So for n less than or equal to k. And that thing is going to, well, should give us back the binomial coefficient that we know. So let's play with Pascal's triangle. So we have 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. So if we're right, if we've got this right, then this thing should give back this thing. So here we are at the fourth level, right? So this is the fourth. So this is when k equals 4. So if k is equal to 4, let's see what happens. So if we have n, let's do it like this. So if k equals 4 and we have n equals 0, then we're going to have 4 factorial. 0 factorial is 1, and then this will be 4 factorial. So that just gives us 1, which is the right coefficient. If k equals 4 and n equals 1, we're going to have 4 factorial, and then 1 factorial, which is 1, and then we're going to have 3 factorial. Okay, let's see what this is. So this is 4 times, well, actually we know what this is. So 4 factorial is just 4 times 3 factorial. So this is just 4, which is what we have here. So that's good too. And then if k is equal to 4, and then n equals 2, what we're going to have, we're going to have 4 factorial, 2 factorial, times 2 factorial. 2 factorial is just 2 times 2. So 4 factorial is 4 times 3 times 2, which is 6, when we do all this stuff, which is this thing right here. Well, I should say that better. 4 factorial is 4 times 3 times 2, which is 6 when we divide by 4. So therefore we get this. So we do indeed, from this expression, get back Pascal's triangle, which is pretty nice. All right, cool. So this guy allows us to expand this thing, 1 plus x to the k for any k. Right? So it's a powerful generalization of this algebraic expansion of 1 plus x to the k, where k is an integer that you know for a long time. and it's coming from what seems like a different source, right? It seems like a different source. All right, next thing we're going to discuss is what range of x will this thing actually converge for. So when does this power series converge? Okay, so we do the thing that we've done several times, change colors. We're going to let an be this k times k minus 1, k minus n plus 1, x to the n, over n factorial. And then we use the ratio test, so we take the absolute value of an plus 1 over an. Right, so we can straight away see we're going to have mod x right here. And what's going to happen here? So on the top, we're going to have k minus 1, dot, 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 and here it's going to be k, and it's going to be minus n plus 1, and sorry, minus n brackets, start again, minus brackets n plus 1, and then plus 1 outside the brackets, so it's just k minus n. Right? And then on the bottom, n plus 1 factorial, and then for the 1 over an, we're going to have n factorial up top here, and then k minus 1, and now we're going to have k minus n plus 1. Yep. All right, let's see what this simplifies to be. So let's see mod x. We will have just n plus 1 on the bottom from the n factorial and the n plus 1 factorial. And then we'll have a bunch of cancellations here too. Right, so we will have all these guys will get killed by these guys right here. Yeah, but there'll be one, okay. So this will go k minus 1, blah, blah, blah. And then there'll be this k minus n plus 1 will be coming just before here. So this guy will be right here in this expansion, right? So all these guys will kill everything to the left of k minus n. So all we'll have here is k minus n. And k is some number, but it's fixed, right? It's fixed. And we're taking n to infinity, right? So as we take n to infinity, what's going to happen to this expression? Well, this k over n plus 1 will tend to 0, and I need absolute value signs around everything. This k over n plus 1 will tend to 0, so we'll just have n over n plus 1. So actually the limit will just be mod x, right? So the limit as n goes to infinity is just mod x. So the series converges, so this series call it star. Okay, so that is using Mclaren series to expand out 1 plus x to the power k. This is the generalized binomial theorem. On the syllabus, or not on the syllabus, but in some pre-calc discussion, there was some mentioning of being somewhat light on this topic because students find this quite technical, and I can understand why. So you will face homework questions on this. I think it's a very good and interesting application of Mclaren series. But but you're not going to be asked to do an exercise like this on an exam, most likely. So don't get stressed if this seems on first glance quite intricate. All right, so let's do another example. So one of the things I promised about Mclaren Series and Taylor Series is that it allowed us to calculate things that were otherwise totally out of range. So this is an example. This is example 11. And it has part A and B. Part A is this. Find the antiderivative of this function as an infinite series. Oops, can't spell infinite. And then part B, evaluate it to .001. Okay, so this is one of the reasons I like Mclaren Series and Taylor Series so much. So look at this e to the minus x squared. It's a very simple looking function. Nothing you know about integration is going to help you integrate it. No u sub, no integration by parts, no trig substitution. Nothing is going to help here. But it's just a very simple looking function, right? This function actually does come up in lots of applications. So this could be a practical problem. We might need to know the area underneath the graph of this function, and all the tricks that we learned in the first half of the course are irrelevant for this, right? But we now have a new tool, and the first thing we're going to do is try to understand this as a power series, right? And we know that e to the x has a power series. That's one of the things we discussed. So this thing is just the function e to the x applied to minus x squared, right? So we could let y be minus x squared and just power series expand e to the y, right? But in interest of time and space, let's do that in one go. So I'm going to have k equals 0 to infinity. We have minus x squared to the k over k factorial, right? Just using the fact that we know e to the x has got the power series expansion and plugging in minus x squared into it. Cool. And then k, so 2k over k factorial. And this is our power series expansion, right? And we also know when it converges, because all we're using is the fact that e to the x converges. And we know that thing converges for any value of x, right? So therefore, we can put in any value of minus x squared into it. It's still going to work, which means that this thing will be true no matter what. So it's true for all x, for all x. So for any x, this power series converges, and it's actually equal to this thing. Wow. So as we've talked about, when a power series converges, it is just as good as a polynomial with respect to doing anything you want to it. In particular, integrating it term by term or differentiating it. So what is this? We're looking for the antiderivative of this thing. We're just going to figure this out term by term. So e to the minus x squared dx. Okay, looks pretty loose now. And then plus constant c. And that is the infinite series that expands out this guy, right? So this is a power series. It will converge. because the radius of convergence of the integrated power series is the same as the radius convergence of the original one, and therefore this guy is our power series representation of this, right? So we don't have an explicit function that we can write down as the antiderivative of e to the minus x squared, but we have an explicit power series, which is actually better because we can do more stuff with the power series when it converges, or at least in the region it converges, than we can with a function. So this is a really good answer, right? It might not be the answer you're used to when you ask the question, what is the antiderivative of a function? But this is really cool. This is really good. And for practical purposes, if we actually want to know some specific integrals, my question here made no sense. So evaluate this thing, the definite integral, to within 0.001. If we want to do this, then we can just deal again with the power series. So let's change color. So that's for part A. For part B, we can integrate it term by term. We already have the antiderivative, so let's take it through. Let's put this 2k plus 1 right here. And then we are evaluating from, is it 0 to 1? I hope so. X. Yeah. And this constant c is just going to vanish because we're evaluating at the endpoints 1 and 0, so whatever the c is, it just disappears. When we're explicitly evaluating some definite integral, we never have to care about the constant c. Right? So we put in the numbers here. Obviously, when x is 0, it's 0, so this is just this series right here. Cool. And this is an alternating series. This is an alternating series. And again, it's not like we can just write down the answer, whatever, 7.63, whatever. But this too is almost as good as that, because an alternating series we can get with an arbitrarily close approximation to its answer by taking a finite number of terms, and we can actually know the gap. We know the difference between the Sn partial sum and the actual answer by this theorem that we know well, whose picture is this. Alternating series going forwards, backwards, forwards, backwards, forwards, backwards, forwards, right? And if we stop here, if we stop here, and so this would be where we are at the Sn step, then this gap here is the Bn plus 1 step size, and we'll be trapped in this region forevermore as we go forwards, backwards, forwards, backwards, forwards, backwards. So the actual S is somewhere here. And so the gap, or the difference between Sn and S, is less than this Bn plus 1 step size. So go back and look at my YouTube video on this if that doesn't make sense. But that's the picture that gives this estimate, which hopefully seems very natural to you, that the difference between the S and the Sn is less than Bn plus 1. So we know exactly how many terms we need to get within whatever approximation, because it's just in terms of the Bn plus 1, which are explicitly given. So in this expression right here, we have Bk is this 1 over k factorial to k plus 1, right? So then S is this sum from k equals 0 to infinity of minus 1 to k. Bk, that's the thing we explicitly want to calculate, and we want it within 0.001, right? So to do that, we need n such that bn plus 1 is less than 0.001, which is the same as 1 over 1,000. Right? Cool. So, what is bn plus 1? i.e., so if we unwrap that, that's the same as saying that 1,000 is less than or equal to n plus 1 factorial times 2 of n plus 1 plus 1, which would be 2n plus 3, right? And then we just try and figure out what's the smallest n for which that's true. So we do some numerical experiments. So actually, let's write it like this. Suppose we have n plus 1. Here I need the notes. So suppose we have n plus 1 is equal to 5. Then we would have 5 factorial times 11, which is equal to 1320. So that's good enough, right? Because that's bigger than 1,000. We're happy with that, but maybe we can get away with less. So this is if. And if n plus 1 is actually equal to 4, then we're going to have 4 factorial, right, times 9. So then 4 factorial times 9, and that is something a lot smaller, 216, which is no good. Okay. So we cannot get away with n plus 1 being equal to 4, right? We need n plus 1 to be 5, which is n is equal to 4. So need, put it down here, need n is equal to 4. Cool. So the question was, evaluate this integral to within this error. Well, we have that the integral is given by this explicit sum right here. So let me just try and squeeze this right here in the corner. We found that S4 will be within that level of error. And what is S4? It's just the sum from k equals 0 up to 4. Okay, and that is some number, right? We have to add up 5 numbers to find out what this is, right? Which we're not going to do, but nevertheless we could do. So if the world just collapsed and we have no more computers and we're back to doing things just by hand and rebuilding society, we can figure out stuff like this because of this powerful stuff, the Mclaren series and the Taylor series. Okay, that's it.